Hello and welcome. Today's lecture will introduce process dynamics. Why are we interested in process dynamics? Because we want to change the dynamic characteristics of a process from whatever it is to something more desirable. What do we mean by process dynamics? It is a systematic study of the trajectory of process variables over time in response to causal process variable changes. I repeat, it is a systematic study of the time trajectory of process variables in response to changes in causal input process variables. The scope of process dynamics includes both the system with no control as well as the system with the controls as well as the process with the control system installed. If we take a look at the room example, when the temperature controller is off, the process input that you can adjust is the heater duty that is input by the user. If a change to the heater duty is made, how do these measured variables change over time? Let's take a look at that. So if a step change is made in the heater duty, and the step change made is a unit step change, 1% change, which is not shown here. At time t equal to 0, the heater duty is changed by 1%. At time t equal to 0, the heater duty is changed by 1%. This is 1%. In response to this change in the heater duty, room temperature will increase, and because the air has gotten hotter, the humidity will decrease because the air will be drier because no water has been added to it. It contains the same amount of water as before, but now is hotter, so it will appear drier. Yeah. So in response to this step change, you can see that the output process variable, there are three process variables: relative humidity, temperature, and odor. Temperature increases, which is the blue curve, increases as shown here by 0.3 degrees Celsius. Relative humidity decreases by about 0.1%. Odor remains the same as before. What's plotted on the y-axis is the change in the process variable from its initial value of rest. Okay, so this is the output process variable dynamics in response to a step change in CHE381a, a step change in the heater duty. If you look at the control system again, the room example again, when the temperature controller is switched on, there are two things that can happen. The operator or user may change the temperature set point, or there may be changes in the Q leaks, Q walls, Q solar, etc. There may be changes in the disturbances, measured or unmeasured. So you are interested in two types of responses when the control system is on. How does the output process variable, which is controlled, respond to a change in the set point, and how does the output process variable respond when there is a disturbance? So there are two types of responses that you're interested in systems with a control system. Response to a set point change. This is also known as the servo response. The response of the controlled variable to a change in the disturbance, which is called the regulator response. Just showing some sample responses. The CV set point at time t equal to 0, this is time t equal to 0. The CV set point is changed from somewhere to somewhere at time t equal to 0 as a step, and in response to this change the control system adjusts the manipulated variable, and this manipulated variable adjustment may be tight or maybe loose, and when you're controlling the controlled variable tightly, one possible response is like this: slight oscillations, and the process ends up at set points. If the control is not so tight, you get a smoother response, but it takes longer for the process variable to reach its changed set point, and you would expect that for tight control you will have to make aggressive changes to the manipulated variable, and so the manipulated variable, the magenta curve here, it's showing very large changes. When you make changes that are slow and not so aggressive, the controlled variable takes its own sweet time in reaching the set point, and the changes in the MV are much smaller. Changes from here both reach the same final value because the final value of the process variable is the same. So the final steady state for both is same. However, the dynamics are different. The trajectories over time are different. The blue dashed curve takes a long time to reach. Changes in the manipulated variable are not very aggressive. The magenta solid curve reaches the set point quicker. However, changes in the manipulated variable are quite large. So this is an example servo response. You could also have, for example, a step change in the disturbance variable. So there is a step change in the disturbance at time t equal to 0. At this time the disturbance changes as a step from wherever it is to a new value. In response to that disturbance, let us say the temperature of the room starts to increase. For example, the number of occupants of a room suddenly increases. 100 people walk into a room. Every person is a 50 watt bulb. The body generates that much heat. So suddenly, because of so many people walking into a confined space, the temperature of that confined space will start to go up, and so the temperature starts to go up. In response to that increase in the temperature, the controller will reduce the heater duty, and this reduction may be aggressive or this reduction may be slow. So when you have aggressive changes in the heater duty, as in the magenta curve, the increasing temperature quickly turns back and returns to set point. When you have not so aggressive changes in the manipulated variable, your process variable deviates larger and slowly returns back to set point. These are typical dynamics that you would have: aggressive control versus not so aggressive control, tight control versus loose control. Now, in order to do a systematic study of basic dynamic responses, a systematic study of process dynamics, you have some basic dynamic responses, and any dynamic response can be reasonably well represented as a combination of these basic response types, these basic dynamic response elements. What are these basic dynamic response elements? We've got the pure gain. What is a pure gain? The input changes as a step, output in response changes immediately as a step. So you may see this as there is an input U, output changes, output is k times U, and if k is greater than 1, if input is changing as a step, output is changing as a larger step greater than 1. You could have a pure delay, that's this chap. The pure delay is nothing but input is the same, output is the same as the input, it's just that it is delayed by a certain amount of time, and here the delay is this guy. So input changes, this black curve, at time t equal to 0, output changes exactly the same way but delayed by this duration. So the pure delay is this duration. Yeah. You could also have an integrator. What is an integrator? Well, an integrator is nothing but, you have a input to a process, you simply integrate the input and that's your output. So u, y. So if you input a step to an integrator, the output would be integral of a constant is a ramp. Output would be a ramp. Yeah. That's what is shown here. Input changes as a step, output is changing as a ramp, and the slope of this ramp is 1. If the change in the input is unity, the slope of this ramp is 1. You also have a first order lag. What is a first order lag? It's shown here. The input changes as a step and the output reaches the same value as the input, final value is the same as the input, but then it slowly rises to reach the final value. This is called a pure lag. These are some basic dynamic responses, and any realistic response can be well represented by a combination of these basic dynamic response elements. Now there are some more basic dynamic elements. Let's see them. You could have a second order overdamped, a second order critically damped, a second order underdamped response, and what you have is there is a step change in the input, output rises from wherever it is to the same value as the input. However, this rise is slow and sluggish. The difference between a second order overdamped and a first order response is, if you carefully look at the initial area in a first order response, and let's just zoom, this is a zoomed view. Second order rate of change at time t equal to 0 immediately after the step will be 0, so it rises like this. On the other hand, in a first order response, the rise will be immediate. You give the time, it will be like this. So the rate of change, I am sorry. So the rate of change at time t equal to 0 in a first order lag is finite. The rate of change in a second order overdamped response at time t equal to 0 is 0. So you have a S-shape-ish response. That's the difference. Second order critically damped, the rise is faster And here the rate of change is again, you have a slow rate of change at time t equal to 0 is 0. Second order underdamped, you again rise and reach the same value as the input. However, now there are oscillations that decay over time. And if you have done your physics, second order overdamped, second order critically damped, second order underdamped responses are observed in a damped spring. You have a spring, there is a mass on it, yeah, and the mass is connected to some resistance which is a damper. So this is a damped spring system, damped spring mass system. These kind of systems, if you have studied in physics, you could have a second order overdamped, a second order critically damped, or a second order underdamped response. Point is, you can have oscillations that die out, or you could have smooth exponential rise to the final value, which occurs in overdamped and critically damped systems. Overdamped system is sluggish, critically damped system is non-oscillatory but much faster. You could also have unstable oscillatory responses. You could also have an unstable non-oscillatory response. You give a step change and the output response just keeps on blowing up. These are some basic dynamic response elements, and any realistic response can be well represented by a combination of these basic dynamic response elements. And just to illustrate these combinations, you can have a combination in series, you could have a combination in parallel. This one is parallel combination of basic dynamic elements, or you could have recycle structures or feedback structures where things are being fed back. This is a recycle structure. Parallel is like this, series is of course series. Yeah. So let's look at lags in series. If you give a step here, this is the input, this output would be like this. Now this output will cause a change in the output of lag 2, but this change would now be because it is being forced by a exponential, this would be a bit more sluggish. And if you give this bit more sluggish response to the next lag, the output of that guy will be further sluggish. So by the time you get here, the output, if this is the time at which the step was given in the input, the output would be something like this, not to scale. So nothing happens for some time, and then of course you multiply by the gain, and then what you get is what is drawn here. You have a step change in the process input and the process output, which is over here. Nothing seems to happen for some time, and then it slowly sluggishly rises to a final steady state value. This slow, sluggish, S-shaped kind of response is very characteristic of many processes in nature. We see a lot of times the slow, sluggish, S-shaped response in chemical processes. What I have here is a lead lag. The second chap is a lead lag, and this is a parallel structure. So imagine input changes as a step. If input changes as a step, the output here will change as a step of magnitude k. Yeah, and let's say this is 1 unit step, this is k. Then this same step, when it goes through the lag, the output would change as a lag, and then you multiply it by 1 minus k. If you multiply it by 1 minus k and k is greater than 1, we are looking at this case, k is greater than 1. If k is greater than 1, then you're multiplying it by a negative number. So this guy will go down like this. You just flip it, multiply by a negative number, and therefore when you add these two signals, what you get is a response that looks, you go to a guy that is greater than 1, and then you go to 1 as a slow exponential decay. So that is this guy, the blue curve. Yeah. On the other hand, if k is less than 1, then what you get is the red curve, and you can think this through. So this is a parallel structure which gives a parallel lead lags kind of structure, where the basic dynamic elements are being combined in parallel. In nature, most things happen in parallel. So series structures are there, parallel structures are much more common. You could also have the basic dynamic elements combined in a recycle structure, in a feedback structure. So what we have is, let's look at this guy and I'll justify why we get the response that we are getting. So let's say the input changes as a step. If the input changes as a step, initially this is 0, in 0 to 1. Okay, if input changes as a step, then this signal has gone to a 1 at time t equal to 0. When you integrate it and multiply it by a constant, this signal starts to rise, the output signal starts to rise, but then you subtract the output signal out of here. You multiply it by 1, so basically you are subtracting the output from the input. This is a summing junction. You are summing this signal and that signal. Now when you start subtracting it, in effect the signal going into the integrator reduces, and it will keep on reducing, and you will settle at a steady state until this signal becomes 0. So when you become 0 and you integrate 0, you remain where you are. So you can imagine you gave the step, output started to rise. Because the output started to rise, the signal going into the integrator reduced, and as it reduced, this rate of rise decreased, and this rate of rise decreased. That's what you get. So a first order lag is actually a neat combination of the basic dynamic elements, integrator, gain, negative gain, combined in a feedback loop. This is a feedback loop. You know, this is a loop. So this is the feedback loop, and this feedback loop gives us the kind of response that is shown over there. So you see, we are calling lag a basic response type, but actually a much more fundamental response type is the integrator. Why do you integrate? Because rate of change, d by dt is equal to something, so dy by dt is equal to something, some function, therefore y is equal to integral of f dt, right? So most fundamental is this integral operator. Yeah. So what we have seen is that these basic dynamic response elements may be combined in series. This was an example of series. May be combined in parallel. This was an example of parallel. Or may be combined in feedback structures. This was an example of combination in a feedback structure. Here's another. Here are some neat combinations. Inverse response, which you will see. So there are a bunch of lags in series. K1 is greater than K2, multiply by -1. So basically this signal and this signal are being subtracted. The speed of lags 2 is much faster than of lag 1. So that means if this signal was a step, lag 1 would be an exponential, but it is a slow lag because speed of lag 1 is much less than lag 2. So it will be a slow lag. On the other hand, this chap would be a fast lag. So this guy would actually quickly go. Yeah. K1 is greater than K2, so this is K1, this is K2, so K1 is greater than K2. So now imagine you flip this signal. If you flip this signal, what you have is, you have a slow lag going up like this, summed with a fast lag that goes like this. So the net response when you add these two signals would be, you go down a bit and then you go up. What do these lags do? These give you these smooth, non-discontinuous S-shaped, this smoothness is because of these lags. So this is an inverse response, a smooth inverse response, not a jerky inverse response, with lags in series, and then a parallel combination of two lags and gains in parallel. The first lag gain is positive, response time or response speed is slow. Second lag gain is negative and smaller than the first gain in magnitude, and the response speed is much faster than lag 1. You get an inverse response. Same logic one can apply to inverse response plus integrator. Oh, okay. So if this was a step, this would be a ramp, and the same step goes through this lag, and again, so this signal would be a this signal would be a negative exponential, and when you add these two signals, what you get is something that goes like this. Something that goes like this. That's what we have here, except that this is very smooth. This smoothness is because of the presence of these lags. If you don't understand why the smoothness occurs because of these lags, just hold on till we do some simulation labs and it will become clear to you. So as you can see, by combining these basic response types, one can get pretty much everything of relevance for our studies, our systematic process dynamics and control studies. So it is very important to understand these basic response types, which we will do subsequently. Can you think of examples in nature that do this, that do this? Huh? I'll encourage you to do that, and I would not like to give you an answer immediately. Maybe you should go and search the net and understand how parallel structures give these very unique responses, how recycled structures occur in nature, how series structures occur in nature. Here's another one. Again, a parallel combination. Pandemic, these days COVID pandemic is going on, right? So if you look at the number of cases, so the black dashed line is virus has been, the onset of virus into humans, and then what happens is the virus spreads quickly, cases maximize, and then they go down until the virus disappears, until the number of cases disappears, because everybody is either vaccinated or has immunity, herd immunity. Yeah. So in this case, this gain and this gain are the same. Lags 1 are faster than lags 2, so what you get is a smooth but fast response here. Lags 2 are much slower, so what you get is smooth but much slower, and this change and this change are the same. I'm sorry, these things are not drawn to scale. So basically what you have is, you got something like this, and you got something that's so much slower, but this change and this change are the same, when you add these two up, you'll get a response that is shaped like this. Let's look at this. How does this come about? You can see that looks like a ramp, but then there are these oscillations on top of that ramp. So what you have is basically a ramp plus a bunch of oscillations. When you add these two, the blue curve is what you get. So that's what this is. If you have an undamped spring system and the mass is displaced away from its equilibrium position, what you will get is simple harmonic motion. You would have studied it in class 12 physics. Simple harmonic motion, and this mass will keep on damping forever and ever, assuming there is keep on oscillating forever and ever, assuming no dissipation, is assuming no dissipation of energy. So you get sustained oscillations, and the description of the equation of motion that describes the motion of this mass, is a second order equation. It's of this form: second derivative of displacement is equal to some restoring, of this form. Yeah. And this equation has a solution which is like this: sustained oscillations that neither blow up nor do they die out. If you add this sine wave to this ramp, this is what you get. Yeah, so you can see lots of things can be done simply by combining the basic response types. Again, what are the examples in nature? So this is pandemic. Where do you see this? I would say life is like this: either you're on a upward trajectory, but then there are the ups and downs of the daily ups and downs, but life has an upward trajectory. Or it could be that you're on a downward trajectory with its own ups and downs. Life is actually usually like this: ups and downs, and either the trajectory is progress or regress. It is never like this. It's never like this. You're either improving or you're deteriorating. That's how it is in real life. Here's an exercise. I give a step. A response is like this. How will you get this? As an exercise, think about how to get this unstable exponential blow up kind of response by combining the basic response types. I will leave this as an exercise for you. A real life example of this? Well, Bhopal gas tragedy, runaway reaction in the reactor. Let's see. Have you got this microphone, no? So you got this microphone. Singer is singing into this microphone, and then you got a speaker. If the speaker is tuned, the speaker volume is too large, what happens is the sound of the speaker goes into the microphone, gets amplified, and then you'll get this boom. The speaker will blow up because of feedback. So a hint is it will have to be a feedback structure. In order to get this, you will have to have some kind of feedback. But this is a real life example. When you have a microphone system, and if the volume is too large, the speaker just goes, it starts to boom, sound like boom, and the speaker, unless you put the volume knob down, the speaker will blow up. That's this kind of a response. Yeah. But how do we get this kind of a response? By combining our simple basic response types. Please do this as an exercise. This brings us to the summary of whatever we have seen. Nature exhibits a variety of dynamic responses. These very large variety of responses can be well represented using a combination of basic dynamic response elements, and these combinations may be in series, in parallel, in feedback, series parallel, series feedback, series parallel feedback, etc. All kinds of combinations are possible. The basic response elements, dynamic response elements that we have seen are pure gain, pure dead time, pure integrator, first order lag, second order lag, and the second order lag can be overdamped, underdamped, and sorry, in the middle there is critically damped. Critically damped. Three cases. And pretty much if you combine these basic 5 response elements, you get everything that is to get there. You may also include pure sinusoids, sustained oscillations, and sinusoids that blow up. Actually, sinusoids that blow up are not required. Yeah, so just a pure sinusoid, undamped spring. You may also include that in these basic response elements, and you, by combining these, you can represent well the dynamics of pretty much any system in nature. With this, we come to the end of this lecture. See you next time. Thank you for your attention.